And thank you all for joining. So yes, my name's Elton. I work for Docker, and I'm also a Pluralsight author and a Microsoft MVP. Before I joined Docker, I spent most of my career as a .NET consultant, so about 12 years, building big enterprise .NET projects. And most of my courses are either around .NET or Azure. But then I worked on a project that had some Docker, and I was pretty much blown away by how much simpler it made everything, from development through to test environments, through to your development tools, all the way up to production. So I thought one day everything will run in a container. And actually, that's why I joined Docker, and that's what this session is all about. So this session is actually a modified version of one I gave at the Pluralsight Live conference earlier this year. I'm going to focus on 5 real-world use cases. So one of the key takeaways for this is that Docker and containers are not tomorrow's technology. People are doing this right now, and the use cases I'm going to show you are what people are doing to get the advantage of containers in production. So lots of demos in this session, but I'm going to get right into what those use cases are. So first of all, cloud migration. So everyone has some kind of plan to move to the cloud, whether it's the next project is going to be cloud native, or we've got a 5-year migration program to get all our apps onto the cloud. The question is, how do you do it in the most effective way? And there are different options. So the example I've got here, let's say I've got 3 applications that I'm thinking of moving to the cloud. Each of them is a distributed application with different components, and right now they're all running in virtual machines in the data center. So typically, when you get to the ops side of these sorts of distributed apps, every component runs in its own VM to guarantee isolation. So to make sure, for instance, that your database component doesn't starve your web server, they run on different VMs. Now, in the case of these example applications, each of those components is running on a different VM. Some are Windows, some are Linux. Maybe that's to do with the technology stack for each component. There's a whole set of different technologies that you have to master to run these things. And if they're all running on different VMs, then the utilization of your infrastructure is going to be pretty small. So most data centers don't get even anywhere near 10% CPU utilization. VMs are so heavy, they use up a lot of infrastructure without actually giving you any value. So if I want to move these stacks to the cloud, well, I've got a couple of options. Firstly, I could go all in on the cloud, and I can look at my the products that are offered by the particular cloud provider I'm interested in. So in this case, Azure. And I can match each component of my application to one of the part of the platform that my cloud provider offers. So this is the first one. So I've got these 3 applications, lots of different components. These are each distributed apps. So currently they run in the data center on each has its own server, each has its own virtual machine. So hugely inefficient, not only in terms of not getting utilization of my infrastructure, but also the number of skills that I have to be able to manage all these things. I've probably got a hybrid team with a whole different set of skill sets just to manage these things. So my first option is I go all in on PaaS. So I look at the application catalog that my provider offers me, and I try and match the right thing. So let's say I've got a message queue and I'm looking to move to Azure, and maybe I'm using MSMQ in the data center. I can move to Service Bus queues in Azure. I can use SQL Azure for my managed database. I can use the managed Redis cache. I've got the API gateway. I've got the app service for running my applications. A whole set of stuff that's all PaaS. Now, this is a really good option in terms of getting the full benefit of the cloud provider. So all of these are PaaS solutions that are running on shared infrastructure. So I'm going to get good value for money because I wouldn't be paying very much unless my apps are working really hard, and I'm getting full use of what the provider offers. But each of these applications, moving them to the cloud is a project. I'm going to have a whole new set of artifacts to deploy these things to the cloud, and I'm probably going to have to change code. So if I want to swap in a different message queue, then I'm going to have to change my code in order to move to the cloud, and that probably isn't part of what I want to do, because as soon as I crack open the code, I need to do a whole bunch of regression testing. The second part of this is, if I do this, I've moved to one cloud. So I've gone through the whole project for each application that's taken X amount of months, and I've moved to Azure. And then if I want to be able to run even on a different region in Azure, that's probably an extra amount of work. If I want to run a multi-cloud and have some AWS as a backup, then that's another project, because all I've done is move to Azure, and I'm going to have to go through the whole process again. So in order to avoid that and to get some reuse of people's existing components, the other option is to go the other end of the scale and go IaaS. So replicate what I've got in the data center with a separate VM for each component, but run those VMs in the cloud, so infrastructure as a service. Now, this is easier and faster because you're going to end up using your existing deployment artifacts. You'll need some setup work to be able to spin up all your virtual machines, but then you can use your MSIs or your jar files or your existing PowerShell scripts to deploy everything because you're just starting with a bunch of basic VMs. And this is kind of portable because if I want to run multi-cloud, then I can spin up some VMs on AWS and use those same scripts and those same artifacts to deploy to AWS. The downside of this is all I've done is replicated the inefficiencies in the data center up to the cloud. And now, as well as having a report that shows me how underutilized all my infrastructure is, I now have a large monthly bill to remind me how inefficient all this stuff is up in the cloud. So the other option, which a lot of people are doing, is moving their application components to containers first. So containerize each part of your application and then run those applications in containers in the cloud. So this gives you the best of both worlds because you can reuse all your existing artifacts. So I'll be showing you some scripts at the moment, which is how you package your application to run in Docker. You can use whatever you currently have. If you have jar files from your CI process or MSIs or whatever you're currently doing, all you can do is write a script to be able to package those to run in containers. And then you can run your whole stack on your laptop or in a test server in your data center or in your cluster of machines in the cloud. It's portable because you can run this stuff in any cloud and you can run it on any infrastructure. So you're going to have, it's also far more efficient to run all these things in containers. So the amount of infrastructure you need to run all your apps in VMs is probably 3 or 4 times the amount that you need to run those same apps in containers. Inside the container, you've still got the isolation. So my application website isn't going to starve my database container because they could be running on separate servers within the cluster. But the cluster itself will be much smaller than having all individual VMs for each of these components. So I'm going to show you a demo of how this looks by taking an existing application and just moving it to the cloud. So this is not a re-architecture. So imagine that this application that I'm going to show you is all up on the source code's all up on GitHub. Each of those components in the kind of pale green box, each of those will run as a container. It's a really simple example voting application. So there's a front end where you can cast a vote. That drops a message onto a message queue. There's a worker that listens on the message queue, gets the request, writes the data to the database, and there's another front end which shows you the results of all the votes. Now, moving this to the cloud, if I put them in containers first, I can just spin up this whole stack using Docker. And that's what I'm going to show you now. Okay, so I'm connected here to a cluster of machines running up in the cloud. So this is a cluster of machines running Docker up in Azure. If I do a Docker node ls, this will list out all the nodes for me. That's all the components of my cluster. And you can see I've got a variety of machines here. I'm going to switch to the portal, which will, it's just a little bit easier for you to see what's going on. It's the same cluster. So if I click on the nodes, I'll see I've got a bunch of Linux nodes, a bunch of Windows nodes, and some of these are working in Docker Swarm, which is one way of deploying applications on the cluster. And I've also got Kubernetes installed, so I could use Kubernetes if I wanted to. This is on the same cluster, so I can use whichever option works best for me. So I'm going to deploy my application. I'll show you how the application looks when you define it to run in Docker. So let's switch to here. And the first one I'm going to deploy. So when you run your application in Docker, if it's a distributed application like this, you need to have some sort of manifest, some sort of file that describes all the components of your application. That's what the file you're looking at now is. This is called Docker Compose, the file format. And all it does is it lists all the different components that I had in my diagram, but in a way that the computer can understand, and it's fairly easy for dev and ops people to work on this definition too. So I've got Redis here, which is my message queue. I've got my database. I'm using Postgres in this example. I've got my vote front end, which is a Python application. and I've got my result front end, which is a Node.js application. I've also got the worker that sits and listens in the background and saves the data, and that's a Java application. So I'm moving all these things to the cloud via containers, but I'm not rewriting them, I'm not changing code, I'm not doing anything like that. I've just packaged up my existing components in containers, and now I can run this in the cloud. So to make that happen, I'm going to copy this whole application definition. And the way I deploy it to the cluster is I create a stack. And a stack is just a set of components that represent one application. This is my Vote application. I can deploy them either as Swarm services or Kubernetes. If you're not familiar with those terms, it's just a way to manage an application running on a cluster of machines that have Docker. Kubernetes is a much more configurable option, but it has a much steeper learning curve because there's a lot more you can tweak. Docker Swarm is a simpler way to get started, but it doesn't have all the features that Kubernetes has. But Swarm is fine for what I want to do. So I'm going to paste in my application manifest that tells Docker what to start, and then click create, and this is going to go off and create all the containers to run that whole application stack. So the way this works when you're deploying an application as containers, the manifest, the list of all the components of your application, that's the desired state. So when I've uploaded this to Docker, it's comparing the desired state to what's currently running. Now, right now, I don't have anything running, so it's creating all the bits and pieces that my application needs. You'll see, if I zoom in here, you'll see there are services for the result and the worker and the vote, and there are also Docker networks. So within this application, all these containers are connected to the same Docker network, which is like a virtual network. So they can see each other by their DNS name. There's a DNS server inside Docker. So when my worker container tries to find the Redis container, it will use the container name and resolve the DNS. But outside of these Docker networks, other containers can't see those applications running. So here's my Vote stack. If I look at the services that are running, we'll see I've got 3 instances of my worker, because that's something I can easily scale out, and I've got 1 instance of everything else, and it's all already running. They're all running across different components, different servers in my cluster. I don't know where they're running, I don't really care. If I look at this component here, one of my workers, there was an error a minute ago, so if I go and click on that, I can look at the containers that are running this service. So these are the individual containers. You'll see here, these are the nodes. So some of them are on Linux node 1, some are on the manager node. These all failed. So if I click on this to see what happened, I can look at the logs. And what I'll find out, these are the logs that have been put out by my application. So these are just standard logs being written to the console. Docker scoops them up and I can view them through here, or I can push them somewhere else. What it's saying is that it couldn't find the database container, and that's because this container started before the database was ready. So 3 of these containers spun up. There was no database for them to connect to, so they exited. And then because it's running in a cluster that manages all these things, Docker immediately started replacements. And these replacements, by the time they'd started, their dependencies were running, so everything's working correctly. So I'll see it's connected to Redis, it's connected to the DB, it's ready to go. Okay, so this is not a terribly exciting application, so don't get your hopes up, but I'll browse now and we'll see what it looks like. So what I have here, incidentally, these application manifests and the Docker images are all public, so you can recreate this yourself. So I'm going to browse to a load balancer. So in my Docker cluster on Azure, I just have a load balancer in front of all the nodes. So if I browse to port 5000, this is my Vote application. I can choose between cats and dogs, which is the perennial question for mankind. And if I go to 5001, this is the result. And it will show me there's no votes yet, so it's a 50-50 split. If I go vote, that sends a message to the message queue. The worker picks it up, saves the data in the database, and by the time I've got back here, I've already got my vote and I can see my results. And I can change my vote if I change my allegiance, and it automatically updates. So it's a pretty simple application, but I've moved it to the cloud without having to go through a catalog of PaaS options. I've moved it all to containers, and this application manifest, this Docker Compose file here, I can run the exact same thing locally. So I can use Docker Compose on my desktop application, either on Docker Desktop for Mac or Docker Desktop for Windows. Use this exact same file and run that exact same stack on my laptop, and it will work in exactly the same way. Okay, so back to the slides. So the first one is just moving things to the cloud. So a lot of customers have a very large suite of applications, maybe 1,000 applications, and there's a set of those that aren't going to change. So they're still being used regularly, but they're not being actively developed. There isn't a project behind them that's adding new features. So I want to be able to package them up and move them somewhere without having to do a whole bunch of regression testing and without necessarily going down a feature set that's going to be actively developed. And this is perfect for that. I can put applications into containers, run them in the cloud or on new infrastructure without changing code. Okay, the second big use case is brand new cloud native applications. Now, I was always a little bit wary of the term cloud native because although it's a useful label for new types of applications, I wasn't sure that it actually meant very much itself. But if you go and look at the Cloud Native Computing Foundation, they have a charter on their website saying what they think cloud native means, and it's actually really useful. There are three assets to being cloud native that they list. One is container packaged. So if you're looking at a brand new type of application, as you're architecting it and deploying it, all the components are going to be in containers. Like that's a must because you need to be able to start these things up in a second and move them around throughout your cluster and have the same experience when you're running on one machine as you get with another machine. And that's just all out of the box with containers. The second one is that they're dynamically managed. So as I've shown you with my cluster, I don't really want to know about my servers or about individual containers. I want to describe my whole application, pass it off to the cluster, and let the cluster manage everything. So we saw that when I started up my application, those worker containers failed to start with. But they were dynamically taken care of. They failed. Docker had saw that they were failed, so my service level wasn't what I'd requested. So it started replacements, and they started up, and by the time they were running, everything was fine. So dynamically managing it means I don't have to worry about failures in my application because it should be self-healing. It should take care of itself. Each container should give enough information to the cluster to be able to tell if it's working correctly. And the last thing is that it's microservices oriented. And that's important because it's an architectural style that lends itself to having lots of small components that can be dynamically managed in containers. And it lets you have different release cycles for each of your components. So as an example, because it's still a fairly new way of developing applications, there's a really good repo on GitHub called Microservices Demo that has this architecture. And each of these circles is its own component that's going to run in its own container, and each of those data stores will run in its own container too. There's a whole variety of different technology stacks here delivering the whole application as a whole. This is a web shop demo application. There's just one front end that's powered by Node, but all the different elements that make the application work together. So the catalog that shows you what you can buy, the user part, which lets you log in, the cart where you store things that you want to buy. Each of those is a separate microservice. It has its own domain, it has a boundary around that, so it owns its own data. So the only way you can get to it is through the API that it exposes. And because of that, each component can use the technology stack that best fits. So in this case, there are some Java components that use Mongo because it happens that a document database is the best way to represent an order. But for the catalog, you probably want a relational database to show how things fit together. So the catalog component uses MySQL. When it comes to orders, there's a queue that tells you whether something has been shipped, and then there's a worker process that listens on that queue and updates the other parts of the data services. So it's a really nice distributed application, and you can go and check out all the code in GitHub, and each of these components has its own Docker file, which tells you how the images get built. The other part of being cloud native is that it's really nicely easy to integrate fantastic open source enterprise grade software in your own applications. So each of those little components that could be a custom component that you write, if you can find a match for doing what it does from the open source world, it's almost certainly already containerized, and you can just drop a component straight in there. So we saw that there was MySQL and Mongo being used by this application. Well, the Mongo team have their own Docker image that you can just drop straight into your application, and same with MySQL. And this landscape here, which I'm obviously not going to go into details on each of these because that will take us way beyond the rest of the day, never mind the hour. It's really interesting that all these application components, most of them are open source, all of them have Docker images. There's stuff like Elasticsearch, which you can just drop straight into your application. And although this is a complicated landscape and it's growing all the time, the world of containers, it's been around for kind of 5-6 years. People have been doing this in production, and there are paths emerging through this landscape that show you popular ways of doing things. So if you're interested in how you monitor your containers, well, you're probably going to use Prometheus and Grafana because those are the most popular, as an example. So let's show you the demo of running that application. So if I switch back to my YAML files. So this is the application manifest for the web application that I've just shown you. This is the microservices app. This is a sock shop. So when we see the web front end, it's just a shop where you can buy socks. And each component is the same format. So each component has its own definition in the services section. There's a front end here with the ports to expose. So when traffic comes in on port 8080 to my cluster, it gets sent to a different port on the container. So I can manage how stuff gets exposed. There's the catalog component and the catalog database. There's a lot more services here because there are lots of small components. And the advantage of this architecture is that if I need to do an update to the orders component, I can just change this part, and the other containers don't need to be updated. Every component can have its own release cycle, its own update cadence, its own scale. So if I need to run lots more orders containers, I can do that. I don't have to scale up the entire application. Now, although this is all brand new, these are all Go and they're all microservices, the way I deploy it is the same as I did with my existing legacy application. So I go and create a stack. I'm going to call this sock shop. And again, I can choose what I'm going to use, but I'm going to use Swarm because that's the one I'm most comfortable with, but I could easily deploy this to Kubernetes too. I'm just taking that whole manifest file, pasting it in here and clicking create. And again, the manifest is the desired state. So this is a microservices application, but Docker doesn't really care about that. It's just got a list of things that it needs to create. It checks what's already there, which is nothing in this case because it's brand new. And so it's going to create everything from scratch. If I were to do an update of this application, and I'll do that in another demo later on, then only the parts that have changed would get updated. So it's a really easy way of doing zero downtime updates because you don't need to do a full regression test of your application. You only need to test what you're changing because you can be confident that only the thing that you're changing is actually going to be updated because you're going to leave the rest as it is. Okay, so that's all done. So now I've got 3 separate things running in my cluster. I've got my own blog. So this is how confident I am in my demos that I don't accidentally destroy my blog. I've got my original Vote application that I just deployed and my new sock shop. So if I go and look at the services here, there are a lot more of them. They're all running on a single container because I don't need the scale for this demo. Everything's been up and running and it's all green. So I should be able to navigate to this now. So let's switch back to my README file. So here's the load balancer, and port 8080 is where that application's listing. So when I browse here, we'll see the sock shop demo. And remember, this is one front end, so the front end's written in Node, but all the back end components are from different microservices. So when I take to the catalog, all this information is coming from the catalog component. I can go and browse at these colorful socks. And if I like the look of them, I click Add to Cart. That then uses the cart component. When I go here, I can see all this information is coming from the cart database exposed by the cart's API. And if I were to log in, this would all come from the user component. So all these separate components, it presents one single application, but it's a really nice way of getting a self-healing application that I can scale independently and update independently. Okay, so I've done the first use case is just moving stuff to the cloud without changing it. The second use case is brand new cloud native applications, getting all the advantages that companies like Netflix have been enjoying with their microservice architectures and applying it to your own domain. The third one is kind of somewhere in between the two, which is taking your existing applications and modernizing the architecture. So I can move them to containers first of all, but then I've got this monolith running in a container, and it would be pretty nice if I could break features down and make it act and behave more like a microservices application without doing a full rewrite. And that's an important point because the big applications, your big .NET applications or your big Java applications, if you were to stop and rewrite them as a full brand new microservices application, that's an 18-month or a 2-year project. And at the end of that 2 years, you've delivered no business value. You've just delivered some technical value. So this is an alternative way of doing things. So as an example, I've got a really basic application here. I've got an ASP.NET website that talks to a SQL Server database. Now, if I'm a new developer joining the team, or if I'm an ops person who is deploying this to a new environment, there's a whole bunch of stuff I need to get ready before I can even run this application. If I want to build it from source, I need a whole bunch of tools. I need MS Build and NuGet and targeting pack and the web development pack and all the rest of it. If I want to run it, I need the runtime. I need .NET Framework, obviously. I need the host, so I need the web server, which is IIS, and I need the database. I need SQL Server. I need the right versions of this. So I need .NET 4.7.2 if I'm using the latest version. And then I need to make sure that I'm the same as everybody else on the team if I'm a developer. Because if I'm using the latest version of Visual Studio and I check in a change to the solution file, I could end up breaking the build because the build server is using an older version of Visual Studio. So everything needs to be in sync. And then even if that is in sync, you're probably not using representative technology. So on your developer workstation, you're going to use IIS Express and SQL Server Express, but in your test environment, you're going to use real IIS on Windows Server and a separate SQL Server database instance. So you don't get the full, you don't get parity across your environments. So the first step to kind of Dockerize this stuff is just to run both of those components in containers. So I can run my big existing monolith in a container. I can run a SQL Server database in a container. And suddenly now these things are portable. I can run these anywhere. And if I compile the application in Docker as well, then the only prerequisite I've got is Docker. So you can write your Docker file, which is the script to package your application so it runs in a container. You can write that so it compiles from source. So it will take your source code, compile your application, then package it into a Docker image, and then that Docker image is how you run your containers anywhere. So suddenly all you need is to download the source code from Git or wherever you're storing it. You need to have Docker Desktop installed on Windows 10 or your Mac, and then you run one command and everything gets built and everything gets run. Super easy. But it's also a really nice starting place to start modernizing your application architecture, to take that monolith and start breaking it down on a feature-by-feature basis. So maybe there's a UI component in this monolith that needs frequent updating. So the business want to change this thing all the time. Maybe it's the home page. They want to change the look and feel of the home page. But because it's a big ASP.NET monolith, to do that, then you need to do a full release. So it would be nice if you could break that apart. And that's what version 2 looks like. So I'm leaving that whole monolith, the big blue monolith in the middle, is completely unchanged. I've got a new component, which is a new container in the bottom left, which is my homepage component. All that does is render the homepage. And then in the top left, I've got a new component, which is a reverse proxy. So all incoming traffic comes to my reverse proxy, and it does the routing between the other containers. So it routes homepage requests to the new container, and it routes all the legacy paths to my original monolith. So I don't need to do a regression test because I'm not changing my monolith, and I just need to test the proxy is routing correctly, and the homepage does what it should. And then the next version, maybe I'm going to break out an API out of my monolith so that other parts of the business can consume some reference data. So I'm going to add a new API component and connect that to my existing database. And then when I get to version 4, maybe I'm moving to something more advanced like event-driven architecture. So my monolith publishes events to say key things have happened. Those go to a message queue, which I'm running in a container. And then I can have handlers that are subscribing to those events and working with the existing database or a new data store. And I can add features by adding new handlers. And all these parts are just new components that are going to run in their own containers. Docker takes care of joining everything together. And these are all super lightweight containers. So I can run this whole stack on my laptop and then run the whole thing again in production on a cluster of 100 machines and scale it up to thousands of containers if that's what I need. Okay, so let's show you how this looks. So there are two things here. Firstly, let's show you the Docker file. So the Docker file is how you package up your application so that it can run in a container. Now this example goes from source code. So there are two parts to this. The first part, the from line here, is saying which Docker image am I using as a starting point? How am I going to start working with my application? And I'm starting from an image that Microsoft own. It's got .NET Framework 4.7.2 installed, and it's the SDK. So it gives me MS Build, it gives me NuGet, it gives me everything I need to compile a .NET application. If you're completely new to Docker files, the words in blue are the Docker file instructions. There's only really half a dozen that you need to learn in order to write a production grade Docker file. And what this is it's a deployment script. It's a script for packaging my application so that I can run it in a container. So I'm starting with this image that gives me everything I need for my tool chain. This effectively is my CI server. I no longer need a CI server with Visual Studio installed because everything I need to build my app is in here. Then I create a working directory called c/source. I copy in the source code from wherever I'm running use my existing build script. So maybe I've got a complicated bunch of MS Build files that I've got a chain together with a batch file that does some other things. I can reuse all of that. I'm just running it in Docker. And so when this stage completes, I will have my published output. I'll have a web application in a folder ready to run. But I don't want my final container to have MS Build and NuGet and all that stuff installed. So my final image starts from a different base. It starts from Microsoft ASP.NET. So again, this is an image that Microsoft own. It's publicly available on Docker Hub, which is where you download these things. And this has got ASP.NET 4.7.2 already installed and configured. So this is everything I need to run my application. So now all I need to do is I switch to PowerShell so I can run PowerShell commands in the Docker file. I create a working directory for the application, and then I run some PowerShell just to create a new web app. And that's telling me which website it's going to be attached to, where the physical content is. And finally, I copy out from the previous stage the published website. So this first stage compiles my application, and the second stage packages it up. So you see this stuff is really easy, and you don't even need to go to source to do this. If you've already got an MSI that comes out of your build script or a web deploy zip file, you don't need the first part. You just start from the second part, copy in your MSI, copy in your zip file, and then you run some commands either to run MSI exec or to unzip your archive, and that's all you need to do. So Docker doesn't mandate you have to use source code. You can use whatever fits for your application. So I've already compiled this, and what I've got is I've built an image which I can use. So version 1 of my stack, this is a Docker Compose file, so exactly the same format that I used for the first demo where I moved an existing application, and the second demo where I've got a brand new microservices app. This is my monolith right now. I've got 2 components. One is SQL Server, so I'm going to run SQL Server in a container, and then the second component is my web application. So this is my monolith that I've built from that Docker file. So you'll see in here there are things that configure how these components talk to each other. So I'm setting environment variables, which I'm using for configuration. Now in here you'll see I've got plain text passwords for my SQL Server user account. And that's also a plain text password in here where I define my SQL Server service. This is obviously not what you would do in production. In production, you can store secrets inside the cluster that are encrypted. And then when you run your containers, that secret gets surfaced as a file in the container, which is in plain text, so the container can read it. But it's encrypted up until that. But just for demo purposes, this is a nice, simple way of getting this working. So the way I deploy this, and remember this actually started live as a .NET 3.5 application, so it could be 10, 15 years old. I just moved it to Docker by writing a Docker file. And now my .NET components are based on Windows Server 2016, because all Docker images are at least Windows Server 2016. So I've done 10 years of operating system upgrades just with my single Docker file to bring my app into the modern world. So again, I'm going to choose Swarm. I'm going to paste in my application. This is version 1. And click Create. And it will do the same thing. It will say what's currently exists. There isn't anything that exists because it's my first deployment. So it will create the Docker network. It'll create the services to run the containers. And these are Windows containers. So they will run on Windows servers in my cluster. I don't have to worry about how that happens. Docker just works that stuff out for me. So if I click on my new service, so my Swarm stack is the one I've just created, I can go and look at the services, and we'll see that these are already up and running. So I've got my database, which is just SQL Server. That's Microsoft's image that I'm just using. And I've got my web application. There are 2 instances of that, one running on each of my servers. Now, when I browse to this application, which I'll do by following the link, so I have a load balancer over my Windows nodes too, which will direct traffic into the containers. So let's browse here. When I hit this application, it's going to take a few seconds to start up. And the reason for that is because this is a legacy application that wasn't built for a dynamically managed container environment. So inside my container, I've got IIS running in the background, and IIS basically has a cold start issue because it expects to be run on a server that is started and left running for months and months and months. It's not expected to be in a container which starts in a few seconds. So there's a little bit of warm-up time while all this happens. But now I get to my application. This is a fake newsletter application. The thing it talks about, Play with Docker, is a real thing. So Play with Docker is an online playground for running containers. You don't even need to install Docker on your machine. So when I click sign up here to sign up for the newsletter, I get a sign up form with some drop-down boxes. And these drop-downs are reference data that's being populated by the application in the database. So the source code for here, this is all on GitHub. I'm using Entity Framework. When it first connects to SQL Server, it's going to find a completely empty SQL Server instance, which is my container. The fact that it's a container is irrelevant. It just connects to SQL Server, deploys the database, deploys the reference data, and then it's able to read it all back. So this is effectively my monolith running in a container. Now, when I update this, so I'm going to move to version 2. So if you remember the diagram, version 2 had 2 new components: a different home page and a proxy, which is going to direct traffic between the components. So my version 2 stack file, this is my Docker Compose file, it starts in the same way. So I've got my sign-up database, which is exactly the same definition. I've got my web application, which is slightly different because I'm not publishing ports anymore. So if you remember, the external-facing container here is going to be the reverse proxy. All traffic goes into that container, and then it routes it to the other containers. So I've got a new container, which is my home page. And my reverse proxy is the thing that has the rules built into it to direct traffic either to the existing monolith or to my new homepage container. So I do my update in the same way. I'm going to go back to my stacks, clear the filter, and create my sign-up stack. And this is when you'll see the desired state business kicking in. So it's going to say that the stack already exists, the network already exists, and some of the containers already exist. So I'm going to have to just work out what needs to be updated. It's going to create the home page and the proxy because they're brand new applications. It says it's updating the database, but actually if I looked at the container, it's the same because it's found the definition is the same, and it's updated the web application. So that's all done. If I go and look at my services now, I'll see for this application, the proxy is still starting up, the home page is there, the database is there, and the web application is there. So I have an error here. So if I go and look at this and check the containers, so again, I will see this one started and had an error. If I look at the logs, oh, it's not going to show me the logs, but it will be the same situation as before. When it started up, it couldn't find the web application container, so it ended, and then Docker started a replacement to keep everything up and running. So if I browse now back to the same port, request now hits my proxy. The proxy directs this request to the home page, and now I've got a brand new home page. This is written in Vue.js just to prove that I am a full stack developer. And the buttons are the same, so I can go to Play with Docker. And when I click this button, it's going to take me back to my original monolith application. Now I get the cold start issue because I'm the first user who's hit the container. There are really simple ways to write your Docker file so that that doesn't happen, and Docker does the cold start when the container begins. But because I haven't done that, now I get into my application. It's the same app as before with the same reference data, but I've got a nice shiny new homepage. I didn't have to change code in my monolith for that. I wrote my new component using the tech stack that I wanted to use. I've got a proxy which is directing traffic between the two. Okay, so modernizing traditional applications. I've got my old apps running, I've got my new cloud native apps running, and now I've got what I'm starting to call an evolved monolith that's running up in my cluster too, all running on the same set of nodes. The fourth one is innovation. So I've got all my existing applications and my current projects that are all running up in containers. But what about the stuff that's coming down the line? It'd be nice to be able to look at things that are becoming reality that used to be just pipeline projects and see if there's something that I can use, but experiment on the same set of hardware that I've currently got. And containers are kind of at the fore of most of the things that are coming to be mainstream that used to be kind of hardcore innovation projects. So, for instance, IoT, that little tiny thing there, that's a miniature Raspberry Pi. If you're running an IoT project, one of the biggest problems is once you've shipped your devices into the wild, they're gone. They may or may not ever be connected to Wi-Fi again. When they are connected, you need to figure out a way to push updates to your software. And that's actually quite a difficult problem because you need to deal with packaging your software. You need to deal with the fact that the device might have a spotty Wi-Fi, so it may be able to get a few packets at a time. You need to deal with reassembling the package once it's got them all, and then stopping whatever it's currently doing gracefully and spinning up a replacement. And actually using Docker for your software that's going to ship and run on your IoT devices takes care of all those problems for you. So the packaging format is already there in the Docker image. The distribution is already there with the registry, with Docker Hub or your own private registry. And Docker takes care of all the unpacking and making sure that containers are restarted nicely. The second one is machine learning. I'm just going to give you some kind of rough ideas for some of these things. Machine learning, one of the problems you've got is how you deal with your models. And you've got different teams working on different models and different sets of data. You can package up your Docker image so that it contains all your prerequisites that you're using. So if you've got a bunch of Python modules that you use, you can package those into your Docker image. You can package a basic data set, and you can package a trained model so that another user, another data scientist somewhere, or an end user can just spin up your container and run it locally without having to find all the bits and pieces that you've used to build up your model and to get working with it. But the one I'm going to focus on for the next demo is serverless. So serverless is kind of the whole world of serverless started with AWS Lambda. This notion that you write some code in a front end on the cloud, you just tell it how to start. You don't worry about servers. You don't worry about how it gets deployed. You don't worry about connecting it with other things. And then, of course, Azure Functions came along as an alternative, and they're both really good. They're both really good options, but they're not compatible. So I can't just take the stuff that I've written in Lambda and then move over to Azure Functions. I need to package it in a different way. I'm probably going to change the code to integrate with other parts of the cloud. But again, what the CNCF are doing, there's a serverless work group within the CNCF who are looking at all the serverless architectures that are out there. And actually, there's a huge amount of commonality. So firstly, they all use containers. So the architecture of these things is very similar. There's some sort of controller. FAS stands for function as a service. There's something that's listening for events that happen. And when that event happens, which could be a blob being created in a storage component, or it could be an HTTP request coming in, that triggers an event, and as a result of that, the controller will spin up a function, which is probably a container. Excuse me. And the second thing that's common with all these serverless approaches is that the pipeline is very similar. So you bring your own code, and then usually the serverless component has its own spec. It defines what you need to do to build a Node application or a .NET Core application. It takes care of the build, so it compiles your code using its own spec, and that is almost always a Docker file that it takes care of for you, and it produces a Docker image. And then when it deploys it, it runs a container, and that's ready to receive the events that the controller is going to send in. And although AWS Lambda and Azure Functions are proprietary, so you can't move them around, there are lots of open source function as a service, serverless components that you can just run in containers. So OpenFAS is very popular. Apache have OpenWhisk. FN is an Oracle project. The one I'm going to show you is the little superhero guy carrying a container. That's called Nucleo. I'm going to show you that now. Now, I'm going to run this in a different way. I'm not going to spin up a bunch of services on my cluster that give me high availability and all that sort of stuff. This is just a project I want to spend a little bit of time on and see how it runs. So I'm going to run a container directly. So here's my connection to my cluster. So let's just check everything's running. So this is the same cluster that I already showed you. This is just the command line connecting to it. So those are all my nodes. Those are my services. And I'm going to run my container. And if you're wondering about where this complicated container run command came from, it's literally copied from the Nucleo website. So most of these kind of fast-moving startup operations, they deploy their software in Docker containers, and they tell you how to run it so you can get up and running really quickly. So this is running in a container on my cluster now, but I haven't created it as a highly available service. I'm just running it as a container so I can try it out. So now if I browse to the URL, and again, this is just a node of my cluster that's running the container. I'll browse here, And this is going to give me the Nucleo front end. It's mostly white space, but this is very similar to what you get with AWS Lambda or Azure Functions. I can check a sample function. There are a whole bunch of different technologies I can use. If I use this Node.js example, and don't worry too much about it being tiny because I'm not really focused on the code. All this does is it receives, it's a REST API, it receives a request and it adds some time to the current time and gives you the response. So if I click deploy, what this is doing now, remember, this UI is running in a container on my cluster where everything else is running. What it's doing now is it's compiling this code into a Docker image that already has Node installed and all the prerequisites, and then it's going to run a container that's ready to listen. So this is ready now, and it's telling me the URL where I can get to this function, which is just a REST API. Now I have Postman here, which is my REST client. So this is the URL that's been deployed from my serverless function. Here's the body of my request. I want 3 hours added to the current time. And when I click send, my Nucleo container that's being managed on my Docker cluster gets the request, adds some time to it, and sends me back the response. And the beauty of serverless is I can go in here and say, actually, I want to, instead of just adding the value that you give me, I'm going to multiply that by 3. And then I click deploy again. And it goes through everything else for me. I don't have to worry about which version of Node it's getting, which server it's running on, how it's dealing with the request, how it's managing getting traffic into the container. It just builds these things, runs them in containers, and now my updated version is ready. So if I run my request again, previously it said 9:45. And if I send it now, I'll get the new response, which is 9 hours instead of 3. So I'm running a serverless component in my cluster now, where I'm also running my modernized .NET monolith. I'm also running my microservices application, which is a full-on microservices app. And I'm also running my kind of legacy application. And thank you for the other people who have voted. I'm running my legacy application, which is Python and Java in there, all running on the same set of containers on the same set of servers. So these are all the components that are running there. And this isn't a huge swarm. There's just a few nodes running here, and you can literally scale this. We have customers who have 600 nodes in their cluster, just running as many containers as they need. Okay, so the last one is DevOps. So there isn't a demo for this because this is more about our cultural approach. So we've covered technical innovation. This is more about process innovation. So when people are moving to DevOps, it's a lot more about how people work together than it is about technology. So if you get a DevOps consultant in, they'll talk to you about frameworks like CALMS, which is a very good way of making sure you're touching the things that you care about. So CALMS is about culture. It's about teams working together. It's about automation to make sure you're not wasting time doing manual tasks. It's about being lean and only doing the work that you need to do, about sharing metrics about how things are going, as well as about what's happening with your application lifecycle, and sharing the work that you've done between teams so you're not duplicating effort. So actually that's great, but it's really hard to do that if you're doing the same set of technology that you've always done before. It's really hard to bring what used to be the dev team and what used to be the ops team together unless they're talking the same language, which they won't be unless you change something fundamental. So the benefit of moving to containers is that Docker underpins that framework, and it gives you something solid to say, yes, we are definitely doing something different, and it's definitely measurable how this is all changing. So the cultural integration is a lot easier when everyone's sharing the same language, which they are when you move to containers, because you build your apps in a Docker file, you define your distributed application in a Docker Compose file. Both of those things live in source code along with your application, and they can be jointly owned by the dev, what used to be the dev team, what used to be the ops team. And that's in a DevOps team, they will be jointly owned. So maybe the devs will write the first iteration of the Docker file, and then the ops will join in and harden it however they want to harden it. And they're kind of jointly owned. Automation is key for this stuff. You can't really build your applications and run in containers unless you're automating it. Like the Docker file, the Compose file, they're all about automating and replicate and being able to easily replicate your deployments. The lean stuff I've kind of talked about already, so you only have to do the updates of the things that you know you want to change. So you don't have to do a complicated set of regression tests, and you don't have to do a full-on rollback procedure if a problem goes wrong, because you can roll back to the previous version, and Docker takes care of all that for you. It can automate the rollback as well as the deployment. The metrics thing is really interesting because as well as having consistent ways of building and deploying all your apps, so you can compare metrics to say how many times have we done a build, how many times were the releases successful. You can also have metrics about your applications in containers. So your legacy .NET application can be producing Prometheus metrics and integrating into a Grafana dashboard in exactly the same way as your brand new microservices application. And the last thing is about sharing. So I talked about the CNCF landscape, all those fantastic enterprise-grade open source components that are already in Docker images. You just can drop straight into your solution. And just to underpin that first point, which I think is the most important about the culture, if you think about a big enough enterprise, there's a whole mixture of technologies. And from the kind of build, package, and maintain on the left there, you've got a whole swathe of different things. So developers are working with MS Build or Maven and NuGet. The packaging is going to be MSIs or zip files, and you're going to deploy with PowerShell or Bash. And then when you come to manage it, there is IIS Manager and SCOM and Nagios, and they're completely different. So the ops team don't work on the same tools as the dev team and vice versa. When you move to containers, suddenly everything does become centralized. So the way you build these things is with Docker files. The way you distribute them is with images. And the way you manage them is with your orchestrator. And the Docker Swarm that I've shown you running on my cluster, and also Kubernetes, you can run those on your laptop using Docker Desktop. So with Docker Desktop, you can spin up a single node or a Kubernetes cluster and deploy using exactly the same application manifests that you're going to use in production. Okay, so I'm going to move on to the Q&A shortly. I will leave this slide up while I do that. Here are some next steps if you're interested in what I've been talking about so far. The demo application that was the ASP.NET application that starts as a monolith and has been broken down into lots of containers, that's all up on, it's on GitHub, and there's a website that walks you through all the steps. That's that workshop. If you're interested in what a container platform is, as opposed to just running containers, that white paper is really useful. And then obviously on Pluralsight, we have a Docker learning path, which has got everything from the 101 stuff that I've just kind of skirted over, all the way up to monitoring in production, which is where you need to be if you're going to be moving to production with your containers. And again, if you're from a .NET point of view and you've got monoliths that you want to bring into the modern world, I have a course on modernizing .NET apps with Docker, which covers that in a lot of detail. Okay, so I'll leave this up and I will quickly switch over to the Q&A. So we've got a few minutes. Okay, so there's a really good question here. So about sticky sessions. How do you maintain sticky sessions with Docker Swarm or Kubernetes? So imagine I've got my application that's a web application. It's running in containers. I've got a dozen containers across my swarm, but I need sticky sessions. So you don't get that for free with your containers because typically you'll have a load balancer in front of all your servers and it will just distribute traffic at random. But if you've got a reverse proxy as your entry point, which you probably will do when you start breaking up your application, then your reverse proxy can do the sticky sessions. So it's not part of the platform that you get for free, but it's actually pretty easy to integrate when you start architecting these things to run in containers. Could you share the difference between a VM and a container? Yeah, good point. So a virtual, the big difference is the amount of stuff that you have to worry about. So if I deploy my application to a virtual machine, I'm going to take my application and I need to deploy all the dependencies that are on that need for it to run. So I need to install IIS and ASP.NET and the right version of .NET. And then I need to maintain the operating system itself. So I've got to do my Windows updates and all that sort of stuff. I've got a VM then with a disk image that's maybe 80 gigabytes that's hard to move around. And I have to kind of nurture it. I have to look after it. I've got to do my Windows updates. I've got to check to make sure that everything's up and running. With a container, the only thing you care about is the bit at the top, your application. So when you run your app in a container, the processes that are actually serving your application, so W3, WP, if it's the case of a .NET web application, that's running directly on the server. The container doesn't have its own operating system. It kind of uses the operating system of the server. So inside the container, your app thinks it's got its own server. It's got an IP address, it's got a host name, it's got its own file system, it's got its own registry. You can set it up however you want to, but actually the processes are running directly on the server. So it's just a container is really just the processes of your application with this thin boundary around it that's super efficient. So if you've got a machine that can run 10 virtual machines, you can probably run 100 containers on there because it's such a lightweight way of doing things. Okay, so what else have we got? You said Okay, yes, so good question here. You said you can run your Vote app on your laptop, but it's a mix of Linux and Windows containers. So actually, no, the Vote application isn't. So there's a Linux version and a Windows version. That's a really good point that right now, if you want to run Windows applications in containers, that has to be running on Docker on a Windows server. And if you want to run Linux applications in Linux containers, again, that's Docker on a Linux server. You can join multiple Linux and Windows servers together to form a cluster, and then you can have a hybrid application where I've got some Windows containers and some Linux containers. They all just reach each other through DNS on the using the container name, and Docker takes care of routing it even if they're on different machines. So that side of it's fine. On your laptop, obviously, you haven't got Windows and Linux. You've only got one of the two. So you can't run a distributed app like that. But you can spin up a couple of VMs if you need to have and run your own cluster on your laptop. Okay, we've got lots of questions here. Let's do a couple more and then see how we get on. Compile with what? Okay, so yes, this is a question about building your application inside a container. So I didn't cover this in any great detail, but in this case, so I'm using MS Build because this is a .NET application. There are, as well as Microsoft publishing .NET images, there's an OpenJDK image, there's Go images, there's Node.js that have the SDKs installed with all the tools you need to build your application. So the structure of your Docker file, so stage 1, I build from source. Stage 2, I package my compiled app to run in the runtime image. That's the same for pretty much everything. So this is a .NET Framework application. Let me quickly show you a .NET Core application. So same structure. The first stage is compiling the application, but this is using the .NET Core SDK, which has .NET Restore instead of NuGet Restore and .NET Publish instead of MS Build. And then the second stage uses the .NET Runtime image and copies in the compiled output. So the structure is always the same. The first part is some image which has the SDK that you need, or you can build your own image with your own SDK if you need that. Okay, so question here, do I need a hypervisor to manage the underlying hardware my Docker environment runs on? So no is the answer. So Docker runs in the background either as a Windows service or as a Linux daemon. So you can have a whole bunch of servers and all you install on them is Docker. So if I'm running Windows, I install Docker, I don't put anything else on that server. It could be a VM or it could be bare metal. I don't need .NET installed. If I want to run .NET apps, the .NET framework that I need comes in the container image. So I can run multiple containers with different versions of .NET, and they're completely isolated. I don't need SQL Server installed because that will come from the SQL Server image. And likewise, if it's Linux, I don't need Java. Excuse me, I don't need Node.js, I don't need Postgres. All I need is the operating system and Docker, and everything else comes through the Docker images. Okay, so any advice for Java build for an old Eclipse IDE dependent application? So let me switch to something else here. Here's my voting app. So this is also an example application that's up on GitHub. And this is a Docker file for Java. So this is exactly the same structure. The first stage is using a Docker image that's got Maven and the OpenJDK installed. And then you copy in the POM file, which is your dependencies, and you do the dependency resolve, and then you do Maven package. So the first stage, completely different tool set, completely different SDK, different application platform, but I'm getting everything I need from this image that gives me this is my CI server, basically. And then the second stage, I'm copying my jar file that comes out. Now, what happens inside here and how difficult it is to move from your Eclipse project definition to a Docker file depends on what you're doing inside your Eclipse files. If you've already got some sort of CI process that is building your application in a headless CI server, then you're just going to take those steps and put them into your Docker file. Okay, so question, the server has to have all of the applications that the containers will need. No, the server only needs Docker and then the Docker images. So I haven't gone into a whole bunch of detail because this is really just more of a kind of overview of what you can do. When you run your Docker, when you build your Docker file, the output is your Docker image, and that is a package of one snapshot of your application. You can have lots and lots of different versions of your applications in different images. And because of the way Docker works, it's super efficient with storage, so they share a lot of the storage for different versions of your app. If you were to take the applications that I've been running, so if you were to take this Docker Compose file, This here is a Docker image that's public. It's on Docker Hub. It's owned by Microsoft. It's got SQL Server Express 2016 installed. And this is a public image that I've built and pushed onto Docker Hub. You can take, if you've got installed Docker Desktop on Windows 10, take this Docker Compose file and do Docker Compose up. It will download these images, and these are quite big images, so the first time you run this, it will download them, and that might take a while, and then it will start up the applications. And no, you don't need SQL Server, you don't need ASP.NET installed, that all comes in these images. So this image is the complete file system for my application, all the dependencies, everything that it needs to run. And so you can run this locally on Windows 10, and you'll get the exact same output that I have when I ran version 1 of my app. And when you switch to version 2, this reverse proxy image is built on Nginx, which is an open source web server. My homepage image is just IIS using Vue.js. And again, you don't need any of that stuff on your machine. You just need Docker. Everything else comes inside these images. Okay, so question, how does Docker decide which libraries will be part of the container? How does it demarcate between the operating system and other runtimes? So Docker doesn't. Docker doesn't care what's inside your containers. So that's entirely up to you. So one of the things that I haven't really touched on, but which is really important, is that all your applications running in containers have exactly the same look and feel. So I've got a whole bunch of things running here. So I've got my Nucleo, my serverless application, which is running which is a Linux container with Node.js. I've got my sign-up web application, which is ASP.NET running on Windows. I've got my sock shop orders application, which is a Go application running on Linux. They've all got the same API. So the way I talk to these things, the way I work with them is exactly the same. I can go and look at the logs, and if there are any logs, this is just whatever's come out of the application. So actually this looks like, this could be our Node.js application here. So I can look at the logs, I can look at the processes that are running inside the application, I can look at the configuration of it, I can see the processes here. It's telling me what's running inside there. If I need to, I can connect to the container. So you wouldn't normally do this, but if I've got a problem and I want to debug, I can attach a console to the container. I can run bash if it's installed, and I can do whatever I need to in here. So I can just get a listing of what's running in there. Exactly the same API to get the logs, to connect to the container, to see what's running, irrespective of what's inside that container. So Docker doesn't mandate certain things have to be in your container image. You decide what you need to get your app up and running. Okay, how are we doing? We're a bit late for time, but I can keep going if that's okay. Let's quickly have a look at some more of these. Okay, so, excuse me, my voice is going, but I'll keep going as long as I can. So what are the good practices regarding stacking dependencies? How do I add extra libraries on top of a basic OS? Good question. So let's say I'm using a Node application and I want to be able to package it in the smallest possible image. Well, you're going to go in, the first thing you're going to do is try and use an official image, which is, let's say, something like, if I go to Docker Hub, and I look at, what's it called? I think it's called Node. So Docker Hub is the free public repository where you can get your images. So there's a Node there's a Node image here, which is an official image. What that means is it's kind of curated by the Docker team and the Node project team. So they write the Docker files to give you the best practices for this. And there are lots of different versions of this Node application. So for a start off, these are different versions of Node. So I've got 8.12, I've got 6.14, I've got the latest 10.12 in here. And there are different variants of it as well. So I've got 10.12 here that's running on Debian, and I've got 10.12 that's running on Alpine. And so the Alpine version is much smaller, so it won't have any unnecessary bloat. The surface area for potential attacks is much smaller, and it's going to give me a smaller image to move around. So this is good for my production. But when I'm working, when I'm doing my build, I maybe want to use the Jessie application because it may have more bits and pieces in there. In terms of how you work out what your dependencies are, it's about how you order your Docker file. So if I switch back to this example here, this is my .NET Core example. Now, even though I'm copying in my source code and I'm building my application, and ultimately that's all I want to do, I could do that in a single step. I'm breaking it out into 2 stages. So I copy in the CS.proj file, which lists all of my dependencies, and I run .NET Restore. And then I copy in the rest of the source code and I run .NET Publish. The reason for that is my source code will change a lot more frequently than my list of dependencies, and my .NET Restore command is quite expensive. So if I haven't changed my dependencies and my CS proj file hasn't changed, there's no need for me to keep restoring every time, because that's going to slow down my workflow. So by putting this section first, that means that this will only run. Docker uses a caching mechanism. So when I'm running through this Docker file, this from here on in, this only runs if my CS proj file has changed. So if my CS proj file hasn't changed, then it will pull this out of a cache, so it won't need to do the restore. And then the rest of it only gets run if my source code has changed. So to get the most efficient Docker file, you pick the right base image that gives you the bare minimum for what you need, and then you structure your Docker file so the most frequently changing things are towards the end. Okay, so I've gone over my time. What I will do is we'll write a blog post that's got the links to the video, that's got a description of what we covered in the session, and I'll answer all the other questions that I didn't get time to answer right now. Thank you very much for joining, and I hope you all find that useful.